Welcome to
Welcome to Sahara, bitch!
Hello everybody, welcome to our video. In this lesson, we will be talking about underdetermination. Are you ready guys? Well then, we are group 2, let's jump right in. Basically, science is often seen as a way how to learn more about our world. However, when we dig deeper, we find a concept called underdetermination. This idea questions belief that science always leads to one right answer, and so that sometimes just using evidence is not enough to pick the best scientific theory.
Underdetermination means that the available observational evidence is not enough to confirm or disconfirm a scientific theory. Scientific experiments require the use of existing scientific theories to test new ones. Because multiple theories are being invoked at once, observational evidence alone may not indicate which theories have been confirmed or disconfirmed. Therefore, observational evidence is necessary to evaluate scientific theories, but may be insufficient. In addition to observations, other factors may be needed, such as the theory's explanatory or predictive power, or its elegance or simplicity.
Underdetermination is a concept in philosophy and science that refers to a situation where existing data is not sufficient to definitively determine or confirm a particular theory and hypothesis. Imagine you have some clues and evidence that can be explained by two different theories. You cannot definitively say one theory is true or false based on the available evidence, as both can correctly explain the data.
One of the philosophical terms that very nicely captures methodological struggles of the sciences of the origin is the so-called underdetermination of theory by evidence. Underdetermination of theory by evidence means that for your evidence that you gathered by observation and experiments, you have alternative theories that contradict each other in theoretical terms, in terms of the terms that they introduce, but they're equally well supported by the evidence, the available evidence. This is not that unusual in other sciences either, but it has sort of a transient, it is a sort of a transient phenomenon, something that after a sort of very severe testing and experimentation disappears, and scientists zone in on one theory that fairly obviously becomes the best available theory. And in physics, for example, it's very hard to even come up with alternative theories often. In sciences of the origin, because of the nature of their endeavor, they gather evidence from various scientific fields, they use very different techniques, and also deal with very meager evidence. Much more meager than scientists would like it to be. They actually encounter underdetermination very often. Usually this period of underdetermination lasts for very long periods of time before they decide that or sort of converge on a particular view that becomes dominant in the field. So for example, in cosmology, there was a big debate between the so-called steady state and the Big Bang theories for about 30 years, when scientists couldn't really determine based on the available evidence gathered with large telescopes at the time which side was really right. That actually started changing substantially in 1965 when the so-called cosmic microwave background was discovered serendipitously by an accident. And only then actually the cosmology started resembling other areas of physics in terms of ever-diminishing underdetermination of the theories.
Talking about underdetermination, there are weak and strong underdetermination. Weak determination refers to a situation in which there are multiple theories or hypotheses that are consistent with the available data, but at least one of them is simpler than the others. In this case, scientists may be inclined to choose the simpler theory as the initial preference. However, they remain open to further research and testing to confirm the truth of the theory.
Now, we will talk about strong underdetermination. Strong underdetermination is a skeptical idea which often used in philosophy. It's used to question our knowledge about many things. As a simpler explanation, imagine that you are trying to figure out if you are dreaming or you are awake. Sometimes, dreams can seem so real that make you cannot tell the difference between them. So, if you cannot be sure you are not dreaming right now, you cannot really know if you are awake. This is an example of strong underdetermination. There are other examples like questioning if there is a real connection between causes and effects, or if everything we see around us is real. In each case, the argument is that we cannot be absolutely certain because there is always a possibility that things are different from what we believe. This kind of skepticism suggests that if there is a rival idea that predicts everything will seem the same as what we believe, then we cannot really know what we think we know. For instance, it's like saying, I cannot be sure I'm seeing an eagle and not a buzzard because they look so similar. However, in everyday life, we often ignore strange possibilities like being a brain in a fart because they don't seem relevant. So, we might question whether we really need the rule or we really need to rule out these strange ideas to know something. In the end, this kind of skepticism challenges our certainty about what we know and suggests that we should consider simpler explanations when there is no clear evidence to decide between different ideas. The next material is about the duhem-quine thesis. The duhem-quine thesis presents a significant challenge within a realm of science, where determining the correctness of a theory becomes a formidable endeavor when experimental outcomes deviate from anticipated results. In the realm of science, theories resemble intricate puzzles, comprised of numerous interconnected components, including the theory itself, fundamental concepts, and initial conditions. When experimental data fail to align with the predictions of a given theory, isolating the precise source of the disparity becomes an arduous task. In response to this conundrum, scientists employ their best judgment to discern the root of the issue. However, the exact methodology through which they arrive at these scientific judgments is not always transparent. Even when experimental results diverge from the expectations set by a theory, there often exist multiple viable explanations for such disparities. The situation is akin to confronting a complex question with numerous potential answers. Philosopher Quine has further complicated this matter by suggesting that even the fundamental tenets of logic and mathematics may be subject to scrutiny when experimental observations are at odds with established theories. Illustratively, the text employs geometric models to demonstrate how our perception of the world can undergo transformation when experiments challenge our previously held convictions. On occasion, disparate theories may yield identical predictions, thereby creating a perplexing dilemma in which it becomes challenging to discriminate among them based solely on empirical observation. Collectively, these factors present a profound challenge that engenders significant uncertainty regarding the veracity of scientific claims. This situation metaphorically parallels the effort to solve a puzzle where numerous potential pieces could fit, prompting reflection on whether one can ever achieve absolute certainty within the domain of science. In essence, the duhem-quine thesis delves into the formidable task of ascertaining the correctness of scientific propositions when experimental results deviate from our preconceived expectations. This challenge leads to a warranted skepticism about the degree of certainty attainable within the field of science.
Next is responses to the strong underdetermination argument. Number 1, the alleged incoherence of the strong empirical equivalence thesis. There are various ways of arguing a strong empirical equivalence is incoherent or at least ill-defined. The idea of empirical equivalence requires it to be possible to circumscribe clearly the observable consequences of a theory. However, there is no non-arbitrary distinction between the observable and unobservable. The most obvious way to undermine the I stated before is to point out a distinction between the observable and the unobservable. It may be then argued that there is no sharp way to draw such a distinction, and that it is therefore arbitrary and cannot bear the epistemological weight put upon it. The point is that there is a gray area between what is clearly observable, like a tree, and what is clearly unobservable, like an electron. So, for example, whether things we can only see with a magnifying glass, like amoeba and tiny insects, are to be counted as observable or not, seems not to be well defined. Number 2, the alleged falsity of the strong empirical equivalence thesis. It may be argued that there is a reason to believe that there will always exist strongly empirical equivalent rivals to any given theory, either because cases of strong empirical equivalence are too rare, or because the only strongly empirical equivalent rivals available are not genuine theories. Thus, the scientific realist is not committed to the view that all the best current scientific theories ought to be really believed, but rather there are at least some circumstances in which we ought to believe in the truth and successful reference of theories about the unobservable. So to establish the I, it must be shown that empirical equivalent rival theories always exist, not just that they do in some cases. Number 3, empirical equivalence does not imply evidential equivalence. Double I is false. Whether or not any of the objections to the I we have considered so far work, many realists argue that double I is false. They argue that two theories may predict all the same phenomena, but have different degrees of evidential support. In other words, they think that there are non-empirical features of theories such as simplicity, novel predictive power, elegance, and explanatory power that give us a reason to choose one among the empirically equivalent rivals. Scientific theories can be said to have empirical virtues such as empirical adequacy and empirical strength. A theory is empirically adequate if what it says about the phenomena or the observable facts is true. So, for example, the theory that all chopper expands when heated is empirically adequate. However, two theories may have differing degrees of empirical strength, even though the weaker one is empirically adequate as far as it goes. For example, the theory that all metals expand when heated is empirically stronger than the theory that all chopper expands when heated, because it entails more prediction or has more scope. It is obvious that part of the aim of science is to produce empirically adequate and strong theories. If you want to know about the world, then scientific theories need to be consistent with the facts, and the more a particular theory can tell us, the better. Number 4. Theory choice is underdetermined. I is true. There are various options if we accept the conclusion of the underdetermination argument. The first one is reductionism.
What is reductionism? Broadly construed, reductionism is an approach to understanding the nature of complex things by reducing them to the interactions of their parts, or to simpler or more fundamental things. It can also be described as the philosophical position that a complex system is nothing but the sum of its parts, and that an account of it can be reduced to accounts of individual constituents. Thus, it is the belief that everything that exists is made from a small number of basic substances that behave in regular ways, and is, therefore, in some respects comparable to atomism. The idea of reductionism was first introduced by René Descartes in Part 5 of his Discourses on the Method of 1637, where he argued that the world was like a machine, its pieces like clockwork mechanisms, and that the machine could be understood by taking its pieces apart, studying them, and then putting them back together to see the larger picture. It is important to note that reductionist thinking and methods are the basis for many of the well-developed areas of modern science, including much of physics, chemistry, and cell biology.
So, should a theory written in French and a theory written in English be regarded as different theories? How are we to draw the line between genuine difference in the content and mere notational difference? Many empiricists have argued that where two theories are observationally equivalent, they should be regarded as different formulations of the same theory. The second one is conventionalism. Conventionalism is the idea that the choice between observationally equivalent theories is a convention, just as it doesn't matter whether we drive on the left or the right, as long as everyone follows the same convention. So the conventionalist argues that the choice between empirically equivalent theories is to be made on the basis of convenience, or perhaps as a result of feature of our cognition, such as the way visual perception or language work. This option is clearly not available to the realists. And the last one is anti-realism.
Moral anti-realism. This is the belief that moral propositions don't refer to objective features of the world at all, that there are no moral facts. So a moral anti-realist would argue that there's nothing about gratuitous violence that's inherently wrong.
Another response to underdetermination is to adopt some form of social constructivism about scientific knowledge. Hence, it is often argued by those influenced by Kuhn and the sociology of science that the underdetermination of theories is broken not by super-empirical virtues but by social, psychological, and ideological factors. Some scientists believe in an order to nature created by God. Some want to defend materialism. Some just want a theory that works because it is needed for technology that is profitable or not, or socially important. Some want to understand the inner workings of nature, and so on. Most realists do not deny that such factors have an effect on the practice of science, but argue that it is swamped by the rigors of repeated experimental testing. Peer review and scientists commitment to be open-minded and skeptical about all the theories.
This material is about constructive empiricism. So there is a theory about constructive empiricism by Van Frasens. He thinks that scientific theories about unobservables should be taken literally, and then true or not in correspondence sense, where the entities they describe are part of the mind-independent work. Note that it saves all the actual phenomenon, past, present, or future, not just an observed so far. So even to accept a theory as empirically adequate is to believe something is more than logically implied by the data. Moreover, for Van Frasens, a phenomenon is actually an observable event, not just necessarily an observed one. So a tree falling over in a forest is actually a phenomenon, whether there is someone or not actually witnesses it. Some key points of constructive empiricisms are as follows. Number 1. The study of the metaphysical is not a part of scientific inquiry. Concepts such as good, and evil fates, etc. are not a part of science. So-called good science and science that is accomplished by way of the scientific method, and the scientist knows what the range of possible answers. The range of possible answers can only include that which is observable. God is not empirically observable, and hence something like the study of God's existence has nothing to do with the scientific inquiry. Point number 2. Scientific realisms believes scientific theories which can lead to the discovery of truth regarding both observables and unobservables. Truth, however, is not in the vocabulary of the constructive empiricist. The constructive empiricist believes science describes what we find in this herbal realm, i.e., that which we can measure and observe. In truth is a philosophical term which has nothing to do with science. Constructive empiricism holds that we don't have to believe a theory is true in order to accept it. The theory can be acceptable, and yet we don't have to believe it is literal. The scientific realist and constructive empiricist can look at the same set of the data, and the realist will claim that the data shows the theory is true. Conversely, the constructive empiricist will claim that the data is only consistent with the theory. Okay, that's all about my explanation. Thank you.